Hello, this is Mr. Yeager for Physical Science. Moving on to conservation of energy and mechanical energy. Obviously, this goes as a continuation of the Intro to Energy video. So these two do go together for the complete energy lecture, essentially. So we're going to look at basically the idea that energy will be conserved. And we're going to look at what's called also mechanical energy. So again, another type of energy, but we're going to see this is just, another type. I mean, we're going to see that it's related to some that we've already talked about. But we're going to be looking at, another way we can describe this lecture is we're going to be looking at energy transformation. So we have to be able to describe what type of energy the object has and what's it changing into as well. So we need to feel comfortable with identifying the types of energies involved. Okay? So for conservation of energy, okay, in the classroom we do a quick skateboard lab where basically this little guy is going back and forth up and down a ramp, and we're looking at the energy changes that occur as it moves up and down the ramp. Just like the cat problem in the Intro to Energy video, we're looking at the idea that when the object is up high it has GPE. When it comes down the ramp it's getting faster, so it's gaining more kinetic energy. Where's that coming from? The GPE goes down, the KE goes up. All right? But the idea is that the overall total energy stays the same. So why is that? We have what's called the law of conservation of energy. What that states is energy cannot be created or destroyed. So the energy that it has, well, it'll always have, but it can be converted or changed into another form. So again, this is why it doesn't matter what type of energy you have, energy is energy. It does tell you what the object might be doing. Okay? So that's what we're looking at some. All right. So we might have you might be looking at these situations on the EOC or on the test. Let's say we have a situation where I have a water bottle that's sitting on the top shelf. Well, what type of energy will that water bottle have when it's up high? It's just sitting there. So does it have kinetic energy? No. Okay. That's not doing anything. It's not moving. It's above the ground. So that means it must have some sort of gravitational potential energy, right? Okay? So like these are the questions you need to be asking when you're given a situation. What type of energy does it have? When it falls, what type of energy is it changing into? All right? And you're going to see we are repetitive in these situations. Instead of a water bottle, the first one was a cat. Now there's a water bottle. Maybe it's a book. Maybe it's an apple falling from a tree. It's, we're going to be using the same energies over and over again. All right? There's only usually about, I'm going to say, 6 to 8 energies that we really need to feel comfortable with and go, it has this and it's changing to this because of what it's doing. All right? So it's always going to be converted into another form. Energy will have some form and then be changed into another form. You need to be able to identify the type of energy changes that occur. Okay? So if we review the main types of energies you're going to run into, and again, there might be other ones out there that you have to pay attention to be able to at least describe, all right? Because I don't have wind energy on here, but where does wind energy come from? The wind. So if there's a blowing wind on a windmill, that must have some wind energy, and what's that wind energy possibly doing? Maybe changing into electrical energy. That's basically the purpose of windmills, all right? But, this can help you out if you just kind of do word association. Kinetic energy is motion. When an object is in motion, it has kinetic energy. It has chemical energy when you're talking about some sort of substance and you're probably about to do something with it. All right? Food is always related to chemical energy. Whether you're cooking the food, eating the food, whatever, it has chemical energy in it. Even the food rotting, that's chemical energy basically. Okay? Solar, light, that comes from the sun. Mechanical energy, this one's sometimes kind of confusing because you see right here, it says, hey, that's motion. So what's the difference between mechanical and kinetic? If you get a problem like this, they're interchangeable. Okay, mechanical energy is energy of motion as well. It's primarily looking at machines doing it, but it can be any object. If I'm running, I have mechanical energy. Potential energy, primarily when we're looking at this, we're looking at the height of the object, but maybe it has elastic potential energy. Remember what elastic involves? Springs. Okay? Electrical energy, electricity. Thermal energy, heat. Hydro always means water's involved. So again, we're going to go through some situations in a minute, and there should be some clear words where it's like a river running through a dam. Well, if a river has water, so that must have hydropower. okay, or hydro energy, hydroelectric energy, etc. All right? So that's what we're looking at, is that we just have to word associate with all of these. The biggest ones people usually forget is chemical. That's probably one of the biggest ones they forget. And then obviously people do get all frustrated that mechanical and kinetic are essentially the same thing. So when you're looking at these problems, I can give you a couple hints, mental notes to take. Identify what the object is doing initially and what type of energies are involved, or what is the object. Like I said, if it's food, chemical energy is in there. All right? Then identify what the object will do afterwards. All right? Is the object on fire? That means there's probably thermal energy. There's probably also light energy. It's okay to have multiple types that it's turning into. All right? That's what we're looking at as well. All right? It's not always one type to one type. It can be one type to two types sometimes. Okay? There's variations to the answers. We just have to narrow those answers down. So here we go. If I have an object falling, okay, what type of energy must it have if it was, it's falling, so we know it's changing into kinetic energy, but it must be falling from some height. So that must be potential energy to kinetic energy. But this, like I said, it's just object. It doesn't matter what the object is. A car using gasoline. So what would this be? Well, what does it have initially? It has gasoline, which would be what type of energy? Chemical. What's that gasoline help the car do? It's helping it move. So that's either kinetic energy or mechanical energy. You'll see it right here. Okay, like I say, kinetic or mechanical. Both answers perfectly acceptable. But chemical would absolutely be the starting point. Turning on a light bulb. Turning on a light bulb. Now this one we could get, again, it depends on where we're starting, okay? If I'm starting at the battery, batteries have chemical energy. What's that chemical energy changing into? Electrical and light and so forth. You can see here though, I don't go that far back. So electrical to light solar, hey, that's fine too. So I guess for this one we would have to be maybe a little more specific and say, with a battery, once you see battery, battery is always chemical to electrical. So again, there's some very common scenarios involved. This one turning on the light bulb. No, it doesn't even say flashlight. So that's probably why I'm being a little silly there. It doesn't say flashlight, so guess what? I agree. This should probably be the only answer to this. Okay. Electrical to light solar. Okay. If I flip a switch, I'm using electricity and it's creating light. Some people could say it creates thermal energy too. I agree. Okay. They create heat. Some other special scenarios we run into. Photosynthesis. That's light changing into chemical. Light creating food. Okay? Solar light creating chemical energy. A generator. A generator is using mechanical energy and creating electricity. A generator helps keep the electricity running. So that's the result from mechanical. Some people in class usually tell me, well, what do I put in the generator? Well, if I put gasoline in, that means it probably starts somewhere else. It starts off as chemical, which then changes to make it mechanical. There's that motor going inside, which then creates electrical energy. Okay? So again, that's why it can be a little tough, because in the end, you're not going to get both chemical, mechanical, electrical, and then mechanical, electrical as answers. You're only going to get one of those two answers. Which one do you think, obviously, we should narrow it down to figure out that either one is correct in the end, all right? So it's okay to think a little bit broader. Just don't be frustrated if you don't see the full picture, all right? And in the answer on the test, it's giving you saying, hey, let's keep this a little more simple. It's just mechanical to electrical. Motors, they always basically use some type of electricity or some type of energy, changes it into mechanical energy. So motors can be chemical to mechanical. I've seen it electrical to mechanical. There's all different types of motors out there. It can be solar to mechanical, a solar-powered car. Okay? Now, what happens sometimes is people get a little confused because, in the end, does all the energy actually get converted? Do we actually get 100% of all the energy changed into the other type? The answer is no. But the thing is, energy must be conserved. So something is disappearing. That's why I have it in quotes. It's not actually disappearing. When I drop a ball and it bounces, the thing is, it's not going to keep on bouncing forever. Technically, if energy was perfectly conserved, I should drop that ball and the ball should come all the way back up to my hand. The thing is, it doesn't bounce as high, and as it keeps on bouncing, it bounces lower and lower and lower and lower and lower, which means, quote unquote, the ball is losing energy. Does that mean the energy is going away? No. Okay, why does the sliding object eventually stop? The answer is, we talked about in the force unit, there's friction. Friction is going to oppose the object's motion. It's going to make it slow down. It's going to try to pull that energy out. What friction always does is it always changes any form of energy, in this case kinetic energy as it bounces, into thermal energy, heat. The thing is that heat doesn't go back into the object to help bring it back up high. It doesn't change back into potential energy. So this thermal energy is pulled out of the ball itself. It's lost from the ball. Okay, that's a pretty terrible looking arrow. So if I have a ball drop, it has gravitational potential energy changing into kinetic energy. When it hits the ground, though, through friction, some of that energy gets lost to thermal. The rest of it goes back into the ball, and it's able to bounce back up again. It goes from kinetic back into GPE. But the idea is there's less GPE now. The ball is losing energy because the energy is going into the ground, it's going into the environment as thermal energy, heat. And what will happen is, over time, as that ball drops back down again, it doesn't bounce as high, it doesn't bounce as high, it doesn't bounce as high, because each time, more energy is being lost to thermal energy. That's all you really have to show with that one. You don't have to get specific with all the breakdowns of the conversions of energy so much. Okay? So friction will create heat, which is thermal energy. All right? And thermal energy is quote-unquote lost by the object to the environment. When I say environment, it's the air, the ground, wherever else it's going. Okay? All right. Basically, the last part of this one, we're going to now break down mechanical energy a little bit more. Okay? So we already said mechanical energy is energy of motion. What mechanical actually is the sum of both the kinetic energy in the object and the potential energy of the object. Mechanical energy is the sum of kinetic and potential energy in the object. It's both. All right? So that's why it is kinetic energy, but it's also potential energy. All right? So all you have to do is just add these two energies together, kinetic and GPE, and that's how much mechanical energy you have in the object. Just add them together. So here we go. If an object had 100 joules of kinetic energy and 200 joules of gravitational potential energy, what's the mechanical energy of the object? Just add them up. 300 joules. Okay. Now, we could get, here's another one. An object has 1,000 joules of mechanical energy and 400 joules of kinetic energy. What's the gravitational potential energy? All right. In this one, I got to subtract 600 joules. Because again, I'll make it very, very clear. Mechanical energy equals kinetic plus GPE. This time I know the mechanical energy, 1,000 joules, 400 joules of KE plus X. X equals 600. I mean, I don't need to go much farther than that. Now, the more difficult thing that could possibly happen is something like this. In this case, they said, the example is a 2-kilogram bird is flying at 5 meters per second at a height of 20 meters. What is the mechanical energy of the bird? So this one sometimes scares people because they're like, I can't just add it. I mean, they don't give me the kinetic energy, they don't give me the gravitational potential energy. What do you have to do? You gotta solve for both. Find the KE and PE with the formulas. So KE equals 1/2 times 2 times 5 squared, 1/2 mass times velocity squared. So this object the bird has 25 joules of kinetic energy. GPE, 2 times 10 times 20, mgh. It has 400 joules of gravitational potential energy. Now that I know both types of energies, what do? Add them up. 425 joules of energy involved. All right? So that's probably as difficult as it really gets with it. All right? Is that we can basically go where you have to find each type and then just simply add them up. Okay? This, I believe, is the last thing, conservation of energy problems. Okay? And this is primarily looking at KE and GPE. We already kind of did this one at the end of the Intro to Energy lecture. Okay? For these problems, we're looking at the following. GPE is going to change into KE. The object is getting dropped. Okay? Or the object's getting thrown into the air. The kinetic energy is changing into gravitational potential energy. Okay? One energy is changing into another, and energy is conserved. So what can you tell me about these two energies? They're equal to each other. The initial kinetic energy that the object has when it's thrown equals the gravitational potential energy that it has at the top of the height. Vice versa, the GPE it has at the top of the shelf is equal to the kinetic energy it has on the ground. So this is where we did one problem already. An object is thrown into the air with a kinetic energy of 200 joules. What's the gravitational potential energy at the top of the throw? The answer would be 200 joules. Okay? They have to be equal. All right? The final example, sorry, I've said last maybe 3 times now, I really apologize, would be actually calculating out the velocity or the height of the object. So for this example, it's giving you the mass of the block and the height of the block. If this block is falling toward the ground, it says, what's the kinetic energy of the block just before it hits the ground? I want the kinetic energy, but I'm not given the velocity. This is what bothers people. They're like, I can't find kinetic energy. 1/2 mv squared, I don't have the velocity. But what can you find? You can find the potential energy. You have the mass and height. And what do you know about the gravitational potential energy at the top and the kinetic energy at the bottom? They're equal to each other. So if I find the gravitational potential energy at the beginning, 10 times 10 times 6, 600 joules, guess what? That's the amount of kinetic energy it has at the bottom. All right? We can then possibly calculate the velocity of the object. We can say Ke equals 600, which equals 1/2 mv squared. We can go 600 equals 1/2 times 10 times v squared. So, I mean, I'm not going to probably be able to complete this in my head. But 1/2 times 10 is 5. 600 divided by 5 would be 120 joules. Not 120 joules, sorry, 120 equals v squared. And then I can take the square root of it. This is going to come out to something, I think this comes out to like 10.9 or something like that. So very, very close to 11 meters per second. Okay? So we could basically solve, that would be the velocity that it has hitting the ground. That would be the most complicated that you can get, where they're making you use the gravitational potential energy formula to then understand that's equal to the kinetic energy, and then plugging in the kinetic energy formula to solve for velocity. All right? Biggest thing overall with this, though, understanding what types of energies are involved, recognizing the changes that take place, and describing those changes, and knowing energy is conserved. If there is friction, energy is lost, but that's all you really need to know about it. Okay? And I believe that is it. All right? Good. Thank you.